Hi everyone. PTP timing and cable. It's literally about time. I mean, really, it's timing we're talking about that we cover this topic. I'm Brady Volpe, founder of the Volpe firm and Nimble This. Whether you know a lot about PTP timing and cable or know very little, it's no problem. We've got two great subject matter experts to cover this topic with us today. First up is Jim Olsen, Solutions Architect, Frequency and Time Systems BU of Microchip. Jim, great to have you with us today.
Thanks, Brady, and welcome to everybody attending. Really looking forward to the session today.
Awesome, Jim. Hey, give us a little background about yourself and where you're from and where you're broadcasting from and what's your background.
I'm originally from Minnesota, and I spent many years in Austin, Texas, but I recently moved in the last few years to Las Vegas. I work more as a remote employee now, and been with Microchip combined companies for many years. Started out with a small company in Austin, Texas, and through several acquisitions, ended up at a very large company called Microchip. So I've been in the timing business for many years. I've written a lot of papers, given a lot of talks at different conferences. So I really enjoy the timing and the timing industry. So really happy to be here to discuss and answer any questions.
Awesome, Jim. Thanks. Next up is Rob Jodrie, Technical Support Manager with Syncworks. Rob, thanks for joining us. And also, go ahead, Rob.
Pleasure to be here. Thanks for having us.
Thanks, Rob. Also, give us a little background about yourself and where you're broadcasting from.
Sure. We're broadcasting out of Ponte Vedra Beach, Florida, which is southeast of Jacksonville. So we're up in the northeast corner of Florida. I'm originally hail from Maine, so the other end of Route 1, and from the northeast. Been working in telecom for just about 40 years now, actually. Started with New England Telephone and Telegraph back in the Bell System days, and all through the different iterations and different companies that became. And I've been with Syncworks now for coming up on 7 years, working in sync. And like Jim said, it's very interesting. It's a very niche kind of a technology and very fascinating. It's interesting stuff, and it's one of those things that runs in the background and keeps a lot of things running. Synchronization and power are things that people oftentimes don't think a lot about, but it is absolutely the lifeblood of the telecom network and cable networks and communications in general. So very, very interesting stuff.
Awesome. Thanks for the intro, Rob, because and I think you hit it right on the spot. Synchronization and power, and we're going to be talking about synchronization today. It's nothing we've talked about prior on this live stream before. Many of your viewers, may or may not know much about synchronization, specifically PTP, but it is something that's becoming more and more prevalent in our cable networks today. We're using it for distributed access architecture, specifically for R-PHY, and many of us, don't have a lot of knowledge about it, even including myself. So this is a great opportunity. We're going to cover this topic in more detail. And I think maybe the way we should start this off is just giving a little bit of the background of, what is PTP? How does it differ from like network timing protocols? And why do we even need it in our cable networks today? So Jim, I'm going to let you take that as a starting point for this discussion. Can you give us a little bit of background of what the heck is PTP and, how did it get started?
Yeah, sure, Brady. So to cover a little bit of history, network-based timing services have been around for a long time. There was a protocol called NTP, or Network Time Protocol, probably 35 to 40 years old. And that's a network-based time transfer technology, but you don't get high levels of accuracy for the time transfer. So if you go back, I think almost 20 years, there was a gentleman by the name of John Eidson, and he introduced a concept called IEEE 1588, which was in-band timing over Ethernet. And if you look back in history, and if you remember the NASA launches when they used to launch rockets and they had the big displays that counted down 10, 9, 8, all those big time displays, and to distribute time was a dedicated copper facilities sending what was called IRIG-B signals. So the idea from John Eidson was to collapse timing in-band into Ethernet. And so for industrial applications like industrial automation or to synchronize robots in factories, where all these devices were connected over LAN technology, this was a technology now where you could do in-band timing over LAN for industrial automation applications versus dedicated out-of-band copper cables just for timing. So that's what really started high accuracy time transfer using IEEE 1588. And then the telecom industry brought it in for the first application being frequency reconstruction with network-based timing services. And when they brought it in from the IEEE world into telecom, they labeled it as PTP, or Precision Time Protocol, for high accuracy time transfer applications.
So what, I mean, when you say high accuracy, what kind of accuracy are we talking about, and why do we even need this? Why do we need high accuracy?
So NTP accuracy is in the millisecond range, where PTP can deliver microseconds or even sub-microseconds of time transfer accuracy. So if you look through the history of, for example, wireless technologies over 3G, 5 to 5G, typically they would use integrated GPS timing receivers in a lot of devices. But in order to eliminate a lot of the complexities and costs and simplify things, they wanted to use network-based time services. But to deliver the accuracy you can get from a local GPS timing receiver over the network requires a high accuracy protocol. And that was the objective of introducing the network-based timing services using PTP.
Isn't NTP, so we already have NTP, Network Time Protocol. Why is that not good enough for us in the networks that we have today, that we have to look at something like the PTP protocol?
NTP is a best effort technology, where PTP is an engineered solution. For the different PTP profiles, there's methodologies you can introduce to mitigate time error as the PTP flows pass through the devices in the network.
Okay. So that, I think, helps us understand the difference between NTP and PTP, or basically PTP is giving us not just a better, higher precision, but it's also, you're saying, giving us a guaranteed clock to our network devices.
Absolutely, yes, a whole different world of accuracy. And maybe a little bit later in the discussion, we can get into some of the details that to help us understand how we can achieve these different levels of accuracy from an engineering perspective.
Okay. So, my first experience of actually hearing anything about PTP was through a company called Symmetricom. And this was when we were dealing with modular CMTSs. And I know there's some cable operators out there that still have modular CMTSs up and running. And Symmetricom was producing PTP clocks specifically for modular CMTSs. How, is Symmetricom still out there? Are they still producing these PTP timers, or what's changed?
Yes, actually, I used to work for Symmetricom, and Symmetricom was acquired by Microchip. So I'm well aware of all those devices. And yes, we did have a specific product for modular CMTS applications, but it was an out-of-band using what we call the DOCSIS timing interface. So we would cable timing to the CMTS modular equipment to align them with timing pulses, but it was out of band. And then when we came to remote PHY device applications, CableLabs wanted a way to do in-band timing, because if you locate the remote PHY in another location, you really can't do out-of-band timing. So the whole idea of bringing PTP into cable originally from CableLabs was to solve that problem of in-band timing to RPDs in a different location than the CMTS location.
Cool. So in our chat room, we just have some discussion right around exactly what you're mentioning. on modular CMTSs. So we have some good friends of ours, Brian Wilson, shout out to you, Levy, shout out to you, and John Downey, shout out to you guys. So they're talking about MCMTSs and how we've used PTP clocks for those, and then also DTI, which you just mentioned, Jim. And also a comment on there, which I think we'll probably explore through the rest of the conversation, where you can have specifically on there 45 minutes if you to reacquire time sync if you lose the timing to the CMTS. And I think that's something we'll talk about later on in the presentation about that. But Jim, or also Rob, maybe Rob, I'll throw this out to you. When we're talking about PTP timing and things like that, we deliver these services into modular CMTSs. There's really critical timing that we have into the CMTSs. So the PTP timer, from your experience, what are the issues that, as we've seen right now, happens when we lose PTP timing into the CMTS?
Yep. So a lot of the CMTS gear that I've been involved with, there's not much in the way of holdover. So the issue is if they lose the reference, there's no sort of internal clock that can keep that service up and going. So a common deployment we have is we actually deploy a couple of master clocks, PTP, so they're connected to GPS, and they're putting out this PTP traffic flow, and then the CMTS locks to it. So it kind of does two things. Number one, it creates that the packets, the PTP packets, so the CMTS can recover time. In addition to that, it provides holdover. So there's a high quality clock in these grandmasters. So in the event the GPS were to fail, a problem with the antenna on the roof, for example, the CMTS doesn't have to handle its own holdover. These clocks provide that function as well.
So basically, Rob, you're saying the PTP timers still need GPSs, but they can function without GPS references?
They can. Yep. We've one of our customers, cable company, they started deploying their network without GPS antennas. So you can. The way I sort of think about that, you have to be cautious with is, so you can actually have grandmasters running just on their inherent internal oscillator quality. With that situation, you sort of create what I think of as sort of a timing island, if you will, in that as long as everything is referencing back to that one clock, you're okay because everything is in sync with relationship to each other. But if you had another grandmaster tied to another piece of gear, and then those two end users were talking to each other, you'd have an issue. There'd be an offset. So that's why as we kind of worked through this process, we found the better solution was to make sure that there was a traceability to these clocks via GPS, or you can also use a boundary clock. We can talk about that later too, but a boundary clock application where you have a grandmaster clock, rather than being tied to a GPS antenna, it is taking a PTP packet flow as a reference.
Okay, thanks, Rob. Jim, back to you. You were talking about how CableLabs, was looking for a solution, a timing solution for CMTSs, and they came on to PTP. Do you know why we actually need this level of accuracy for our for our modular CMTSs, but more recently, we're really relying on PTP for our distributed access architecture, for for our remote PHY solutions and related technologies?
Yeah, Brady, good question. And the clocking rate between the MAC and the PHY must be very close, or you're going to have a lot of problems with video transmission streams. So CableLabs standardized on a PTP profile called G.8275.2. G.8275.2 is a layer 3 unicast profile. We can talk a little bit later, but there's additional profiles that are more accurate than G.8275.2. But the remote PHY application itself requires a 1 millisecond alignment between the CMTS equipment and the remote PHY equipment. So that's not a particularly stringent accuracy requirement, 1 millisecond. And it's a relative requirement between the CMTS equipment and the RPD equipment. But PTP allows you to reliably synchronize the two devices together. As long as the network is up and running, you should be able to provide that level of 1 millisecond or better alignment. So the PTP flows in the layer 3 unicast model go through the switches and routers. And we can easily achieve a millisecond even through 5 or 6 routers because it's not a super stringent requirement. But as Rob said before, what's really important for this is not just the PTP flow and the accuracy, but it's also features like redundancy. Because as you talked about, if you lose your source of time or PTP flow capability, and you allow the CMTS and the RPDs to diverge from a timing perspective, it leads towards outages. So redundancy, reliability are even more important for these applications than accuracy. So we can easily achieve the accuracy requirements with that PTP profile. And as long as it's engineered in a resilient, redundant fashion, you're pretty much guaranteed to deliver the accuracy needed, so you will not end up having any outages.
So I want to drill in on that for a moment, Jim, because I think what you talked about is really important for in particularly operators and anyone working on a CMTS to realize. I have a non-redundant PTP clock, and I unplugged it from my CMTS just for a short period of time in order to take a picture of it. And during that short period of time, my modems went offline. And I didn't think it was going to be that problematic, but I think knowing that if maybe you as a guy working in a head end, you think, oh, I'm just going to unplug this cable from my PTP timer from the CMTS to move it, or maybe replace a cable, do some maintenance or something like that, and it's going to be very brief. I'm not going to cause any issues, but in actuality, it can cause an outage. So what's your experience, or so both to Jim and Rob, what are your experience and what are your recommendations if you have to do some type of maintenance like that when you're dealing with maybe removing the PTP timer from a CMTS, whether it's an MCMTS or a DAA based CMTS?
Right. Well, as Jim said, I mean, the big thing is resiliency, redundancy rather. Working with another customer actually this week, and there's an issue where they have a grandmaster that is providing time to the whole network. And there's an issue we have to get at, similar to what you're describing here. And the problem is they're not pointed to two different grandmasters. So we typically see where in the clients, you can point them to two different grandmasters. So if that were the case, you could take one down, upgrade it, work on it, do what you have to do, and the other would pick things up. We're in a bit of a quandary with this one because when we do the work on it, we'll take that down and those clients will be impacted. So the upfront network design is really important. You've got to kind of look at, what's service, what's the application, what are we doing here? And then exactly, how does this hold up from a redundant standpoint? Because if you've just got one clock and you have an issue, you've got an outage. And as you saw in your lab, it doesn't take long for those units to go down. There's virtually no holdover to them. And to your point, back in the old kind of legacy bits world, you could get away with that kind of thing. They had high quality oscillators in these bits clocks, the timing signal generators, and you could take a reference off, and depending on what the oscillators were, whether they're rubidium or quartz, you'd be good for days, if not weeks. And you could mess around with the front end, but not the case based on my experience in CMTS. That stuff it needs an input. It needs an input from a device that has a high quality holdover, and if you have that, you're in good shape.
Yeah, it was shocking. I mean, the outage was almost immediate. So I think that's something, if there's one takeaway people have, these PTP clocks are really, really important. So I think if what you're saying is that best practice is to always have, redundancy, I think that's really, really important to understand from that. So Jim, you talked about sort of, the next steps in the evolution of PTP timers and where we're going of that. So there's, a lot of talk in the industry in 5G and what we're doing with that. What are your thoughts there?
So that leads into some really good subject matter, because G.8275.2, the layer 3 unicast profile we talked about, the PTP flows go through the switches and routers. And we can do a millisecond of accuracy, but very difficult to achieve extremely high levels of accuracy. In 5G, typically the target is 1.5 microseconds or better accuracy to absolute UTC GPS traceable time. So over a network of several switches with PTP flows going through the switches, there's going to be some level of time area introduced by the switches themselves. So the industry standards bodies and the associated vendors created another PTP profile called G.8275.1, which is a layer 2 multicast profile. And that profile introduces the concept of what we call a boundary clock function. But if you look at the problem with transferring high accuracy over a network, it's related to what we call network asymmetry. Network asymmetry is the difference in delay between the forward and reverse direction of a PTP flow from the grandmaster server function to the client end user application. So Brady, let's say I am a PTP grandmaster clock server and you're a PTP client. And the network between us is where we're trying to do the time transfer over. So to understand how asymmetry impacts time transfer, I'll try to provide a simple explanation. So the first step in the process is I'm going to send a timestamp from myself, Brady, to you. And then you're going to turn around and you're going to send that timestamp back to me. And you're going to ask me as a grandmaster PTP function, can you measure the delay and make a correction for it and send me a timestamp with a correction for that delay so we can be time aligned extremely accurately so the time transfer can execute down to a microsecond level or better. As the grandmaster function, I say, sure, I can do that. But the measurement I make is going to be a round trip delay measurement. I do not have the ability to say exactly what the delay is in the forward direction or the reverse direction, but I have a GPS antenna connected to my head, so I can calculate the round trip delay very, very accurately. So when I send the timestamp to you and you send it back to me, I'll execute a round trip delay measurement. Let's say that round trip delay measurement is 10 microseconds. What I can then do is I can divide that measurement in half and assume the forward direction is 5 microseconds and the reverse direction is 5 microseconds. So I can make a 5 microsecond correction to my timestamps in an attempt for us to become now extremely accurately time or phase aligned to UTC absolute time. But what if there is asymmetry in that connection to where the actual forward delay is 4 microseconds and the reverse delay is 6 microseconds? That's 2 microseconds of asymmetry. So if the forward delay is actually 4 microseconds, and based on my round trip delay calculation, I'm going to send a 5 microsecond error correction to you. We have just introduced a time transfer error of 1 microsecond because of the 2 microseconds of asymmetry in the difference in the delay in the forward and reverse direction. So asymmetry is the problem with high accurate time transfer.
And isn't asymmetry pretty much more the typical scenario that we would have than a symmetrical network?
Yeah, some TDM networks were symmetrical to some extent, but all packet-based or Ethernet networks have fairly high levels of asymmetry. You never see the same delay in the forward path as the reverse path for many different reasons. So G.8275.1 has a methodology to mitigate the time error introduced by asymmetry of the devices in the network themselves. And that methodology is called a boundary clock function. The terminology for a boundary clock function for switches and routers that have a boundary clock function is called full on-path support for PTP. So the biggest difference between the previous profile we discussed, G.8275.2, and the G.8275.1 profile is the 75.2 profile traverses through the switches and routers. The 75.1 profile with the boundary clock function is terminated on one side of the switch or router and regenerated on the other side. So we recover the clock on one side and inject the clock on the other side. So the degradation of the timing does not occur when the PTP passes through the switch or router because it does not pass through the switch or router. So this is an attempt to mitigate the asymmetrical time error introduced by switches and routers. So boundary clock functions for 5G application to deliver highly accurate timing like a microsecond, very common now. And there's different classes of boundary clocks that have different levels of time error mitigation. And the technology is getting better and better. And the classes now we're introducing can produce less than 5 or 10 nanoseconds of error per device. So it's getting really good, which allows us to have longer timing chains, meaning the grandmaster function can go through more switches and routers than it did previously to deliver those highly accurate numbers to the end user application, which is very stringent in 5G mobility and fixed broadband wireless applications.
So is this like, so I've heard of PTP version 2. Is this all part of PTP version 2 that you're talking about, or is this even an extension beyond PTP version 2?
It's really an extension beyond PTP version 2, full on-path support. And there's actually some new stuff coming out along with security and other things related to PTP as well. But to solve the accuracy problem was the biggest thing for 5G, to use PTP as a network-based timing services for mobility or 5G applications. And they've pretty much solved it. We have been very successful now delivering network-based timing services using PTP to meet, microseconds over many switches and hops in networks all over the globe.
No, it's very interesting, Jim. I want to take a couple of questions that have coming in on the chat room. First off, from John Downey, he brings up an interesting point where we have CCAP or CMTSs today that can support both the traditional integrated CMTS solution as well as RPDs. And John's question is basically saying, his concern is this is a concern now because you have the legacy CMTS and now you're introducing a PTP timer to support the distributed access architecture, the RPD that's out there. So my question to both Rob and Jim is, have you guys run into this, and do you see any challenges with this type of integration?
I guess I could try to field that one. With flexible MAC architecture, really see now the emergence of two things. One is the RPD, the other one is the RMD, or the remote MAC-PHY architecture. We're seeing now CableLabs really standardizing both methodologies for the flexible MAC architecture. So really the RMD, or the remote MAC-PHY deployments, is more like a mini CMTS, much further out towards the edge of the network. So PTP certainly solves the problem from a CMTS head-end location to a remote PHY location. And if you have a RMD, a remote MAC-PHY device, you have the MAC and PHY in the same device, so they already share a common clock. But there's other reasons to bring PTP timing into those types of devices, and a lot of that has to do with video. For example, we know one vendor of RMD remote MAC-PHY devices that uses PTP because there's two video modes. One is video sync mode, and the other one is video asynchronous mode. where the 6 megahertz multi-program transport stream is impacted by synchronization, where you can reduce the amount of overhead you use if you synchronize those 6 megahertz streams in a remote MAC-PHY type application. So I think standardizing on PTP across the board, distributing it from the CMTS and actually consuming it at the CMTS and consuming it downstream to an RPD or RMD location is going to be a very standard practice. And then the next question from an evolution perspective is, what do you do then if you have to add 5G services, mobility or fixed wireless broadband? You know, what do you do then? And what profiles for PTP do you use from a network-based timing services perspective to achieve the additional accuracies that you need for the 5G applications?
So that's interesting, Jim, because you're getting into some of the additional questions that have come into the chat during the conversation, which is, do we need PTP on the MAC-PHY? And I almost think that there's, or the R-MAC-PHY, remote MAC-PHY. And it seems like there's a little bit of discussion going back and forth on the chat room where some people are saying maybe we don't need, you know, the MAC-PHY does not need PTP. But I think your comment is interesting where you're saying, well, if we start to deploy 5G off of a MAC-PHY, then the need for PTP becomes even more critical. So I'd like to pose the question out to both you and Rob: is what is your experience on the need for having PTP timing at the MAC-PHY? And I think then if also if we don't have PTP at the MAC-PHY, as some of the folks are discussing in the chat room, what do you think, you know, how does that impact it then if we have remote MAC-PHY without PTP when we want to just start deploying 5G?
Yeah, I guess I can try to take that one too. So technically, the remote MAC-PHY does not need PTP because the MAC and PHY share a common clock in an integrated solution. But as we discussed, just one angle of it is the video. You can, there is benefits to running video in a synchronous mode. But also if you're engineering and you're a cable guy and you're looking forward to the future, you could run just relative PTP timing, meaning no GPS connected to the grandmaster, and achieve phase alignment between a CMTS and an RPD, and also provide a good clock for video sync mode operations. But if you look forward in the future, the 5G timing requirements are absolute traceable requirements to UTC or GPS time. So that's one reason to factor in ahead, putting GPS in ahead of time, is to prepare for the future. And the second, for PTP services out of a CMTS head-end location. At some point, whether it's for fixed wireless broadband services or for mobility services, the cable companies will certainly be offering these services in the future. So how do you prepare your network for that? One is UTC traceability to GPS. The other one has to do, related to 5G, with interesting advancements in technology for both DOCSIS and for the PON segments of the network. For example, the new DOCSIS technologies allow for the introduction of what we call the DOCSIS timing protocol. And in PON networks for GPON for access, which could also be used in the cable markets, both of those network segments now can be used as a boundary clock function. Using DOCSIS timing protocol, the DOCSIS segment can become a boundary clock function, as well as a PON access segment in cable networks could be a boundary clock function. So this helps enable us to deliver high accuracy PTP to mobility or fixed wireless radio technology for end user applications in the cable markets. Certainly this is the evolution that we're moving to. And so the question for the cable architecture, as you advance Ethernet further and further out into the network, we can use full on-path support technologies in the transport network, and things like boundary clock functions in the DOCSIS or PON access parts of the network to deliver extremely high accuracy to the end user applications in the future.
Okay. So basically, it depends really with MAC-PHY, right? Whether or not we need PTP for depending on what type of applications we're throwing after the MAC-PHY, from your perspective, right?
Yeah, that is correct. Whether we're streaming video or not, maybe it's just a broadband internet connection services, not so important. But if we're doing high quality real-time video applications, you might want to look at running video sync mode through those types of devices.
And then another thing that's really important in the cable industry, we're starting to talk about, are things like low latency, and then LLX, or low latency for 5G. I think that's also an area where PTP becomes more important. So Rob, I'd like to throw some questions your way. When we talk about like sync evolution, and also you've talked about some things like GNS or GNNS or GNSS. As being something that can be a single point of failure. So things like GPS satellite integration and stuff. I know you have some best practices that you've discussed previously when we were getting ready for the show. Can you talk us through some of those?
Sure. Yep. So yeah, that's a conversation comes up a lot. GNSS vulnerability. There's issues with.
And specifically, what is a GNS vulnerability?
Yep. So one thing would be that you hear about is jamming. So there's so first of all, when the signal arrives from the satellites to the actual antenna, it's a very low power signal. So it's very easy actually to jam that and block that signal. So that's kind of one concern. There's also environmental issues in the atmosphere that can impact GPS. Those are a couple of the heavy hitters. There's other issues. One you hear about is actually spoofing, which is a pretty sophisticated, involved process, but they can actually create a situation where the GPS receiver might think that it actually sees the real satellite constellations, and it does not. So that's pretty sophisticated, and really jamming is kind of the big issue, and also weather. Then of course, if you've got your antenna out on a roof in the weather, that can be a problem too. So there's a number of things that can impact that GPS reception. So, and you were talking about network, first of all, kind of, looking down the road of, what do these new next generation sync devices do for us? And the answer is a lot of things. So we're having a lot of luck with cable, and also with our telecom customers, where we'll deploy these devices. And in a lot of cases, many of the services that we might deploy in other customers' networks, they don't have the need for it right now. But the nice thing about these systems is you can use them as simply as a GPS receiver, and this is capable of generating T1 signals that you can use to drive a legacy bit system. So that's kind of nice. With a network evolution from TDM-based network to packet-based, in a lot of cases, the transport system, the old legacy SONET TDM-based stuff, is being decommissioned and removed. And in some cases, those network elements were actually providing the timing references to bits clocks. So you've got the situation where you're migrating, evolving your network, and you're actually running a situation where you don't have access to these references that you used to have. So the nice thing about these systems is a couple things. You could take and put, a GPS receiver, a next generation timing system with GPS at location A and B. So that's all great. You can time your bits clocks there. They're capable of doing NTP and PTP. But another really nice thing is that you can actually use PTP, not so much for an application, like to reference a CMTS, as we talked about. You can actually back up the GPS from site A to site B. So you can configure one of these Ethernet ports at, for example, site B as a client, and you could take timing from site A to B, make that the secondary reference. And in the event that the antenna blows off the roof at site B, you're not now in holdover. You still have a stratum of traceability via the GPS antenna connected to site A. So a lot to unpack there, but the nice thing is you can very simply fire these up, time bits clocks, and it's a very forward-thinking device in that we have customers who are looking at 5G. They're not there yet. That's great. You haven't got to put something in your network today that needs a forklift to remove an update down the road. It's got applications for today and it's got applications for down the road. And you can actually back up this network as you strategically locate these systems. So.
And how critical is, because I mean, we mentioned earlier, maybe not even using GPS, but how critical is it to constantly have access to GPS for reliable timing on the PTP network?
It's very important, so it's important to be traceable to GPS. And again, like I was saying with that redundancy configuration, it's the nice thing is you continue to have your connectivity to Stratum 1 via another system's antenna. So, for the longest time, the answer in the telecom network, and a lot of networks, was put GPS everywhere. I mean, that's fine, and that is a solution. The problem with it is sometimes there's issues of GPS reception. Sometimes you're in an urban area where you may not own access to the roof. So putting an antenna on a roof for your GPS receiver is an issue. So these boundary clocks that we can deploy are a way of putting a system in, reference it not from GPS via a locally deployed antenna, but actually using PTP from a device that is tied to a GPS antenna. So you've got, when you log into the system, you look and you'll see it's carrying a clock class of 6, for example, and that's telling you that it has that UTC traceability. So if you deploy it that way, sprinkle these systems around your network, it's redundant, resilient, and you haven't got to worry about losing that reference and then getting into a situation where you're in holdover, you're now drifting and having those kinds of service impacts.
So you're mentioning the inability to always have access to GPS. A good friend of the show here, Brian Wilson, mentioned maybe Starlink, and Starlink is the SpaceX internet service that's out there, could potentially replace GPS. And another friend of ours, Ildefonso, mentioned that maybe Starlink won't have the necessary thing, the necessary timing. But then Brian Wilson has shot back that it's potentially already been used. So I'm curious if you guys have heard or looked into anything as to whether or not Starlink could be a clock reference usable by something like PTP.
Not that I'm aware of.
Yeah, this is Jim. That's an interesting question. And there's different satellite systems out there now. There's low Earth orbit and other satellite technologies that deliver, supposed timing services. And one of the things that a lot of the big operators have looked at is, can you use this as an alternative or a backup to GPS? So many of these satellite services, where do you get your time from? They get their time from GPS. So you're just really adding another layer. And in many cases, a lot of these satellite services are just that, services, and they're subscription-based services. So taxpayer dollars pay for GPS. And so it's a free service once the taxpayers fund it. And the satellite-based services for many are going to be subscription-based services, so you really have to pay additional money for it. But all of them are really, they extract their time from the same thing, which is the GPS satellites, which are controlled very, very finitely from the GPS ground stations. They actually use a lot of the microchip, cesium, and hydrogen maser technology to produce the accuracy and the uplink to the satellites to achieve the UTC traceability. So it's another layer, and it could be a backup or alternative. It depends on what you're looking at. If you lose the GPS satellites, or somebody hacks in and the ephemeris data is not available from the satellites, having another satellite backup system typically is not going to help you, because they really rely on GPS also.
And one quick thought too is another deployment we do, and I think this is actually a kind of a better design or solution to this issue, is we have what they call it's an area timing hub. So basically, we'll have a GPS receiver connected to GPS, obviously, and you can back that up with a cesium clock. So what that is a highly accurate stratum untraceable signal that you can feed into this device. And now your situation is, if you were to lose your GPS visibility, rather than the device going into holdover and running on its rubidium internal oscillator, now it's being disciplined by this cesium clock, and it can virtually, I mean, drift no longer is an issue. Now you've got your PTP traffic flow out to the world from this device. And again, you're being disciplined to this cesium clock. We do that as well. We kind of get into these area timing hubs. So you'll find your core center, and then you will GPS. And one more other layer is there's actually a firewall product Microchip makes, where they can actually detect jamming, spoofing, and you also use cesium in that deployment. But so you've got this firewall, if you will, between the antenna and the receiver, and then you have a cesium backup. So the receiver sort of via this firewall can determine when it needs to cut itself loose from GPS for whatever reason is being impacted. And now you've got this device continuing to put out UTC timestamps. It's sort of, I mean, the way I think about it is it knows what time it was when it lost the reference, and now the cesium just keeps it incrementing at a proper time, and virtually could run indefinitely. So that seems to be a more viable solution, I think, for a network that has to have time, can't be drifting, and
Yeah, and I think, I mean, it really goes to show how important our PTP timing is when you're starting to indicate you're getting backups to your backups, you're having firewalls that are detecting vulnerabilities. And there's no question that our DOCSIS networks are just becoming very, very critical. We're trying to maintain very high availability into them. I think the question I have is, do these clocks go bad? And if so, how do we detect it, and how do we troubleshoot it if a clock goes bad?
Right. So there are, there's, first of all, these all have remote monitoring capabilities, so they can report alarms to a NOC center. You can log in remotely, and there's a lot of reporting. I mean, they're like any device. Do they go bad? I mean, everything will eventually. These systems, again, are built with some backup, so that if thing, and again, this gets back to the issue of the redundant deployment sort of upfront. You're building in protection for that scenario, but there's certainly alarms that report, and switching can occur, and then you obviously log into the device, show alarms. What are you seeing? The most common issue we bump into is antenna related, actually, not internal failures, but when we bump into problems, the issue is there's an open antenna alarm that you've got to chase and figure out connectors and coax. So most of these devices, once you get them basically configured and fired up and operational, the variable becomes the coax that goes up onto the roof of the GPS side of things.
Are there any other things that we should be looking out for with respect to PTP timers, Rob, that we have not covered?
Well, there's a couple design considerations. One to sort of point out is with the GPS receiver, for example, you've got an antenna on the roof, and you may have a one-story building. So you may have a piece of coax that's 20 feet from the receiver to the junction box. Then there's a surge arrestor that we install to protect from lightning. Then you might have 10 more feet of coax. You may also be in a 20-story building, and you may have hundreds of feet of coax. So one thing to bear in mind when you're doing this, especially when you have a time-sensitive application, there's a cable delay setting that you have to be aware of. So basically, it's you tell the device effectively how far away physically is the antenna from the receiver, so it can compensate for that propagation delay. So a couple of considerations. One is distance, how long is the cable, and also cable type, whether it's LMR 240 or 400. There's different numbers, but basically you tell the device that there's a delay of this many nanoseconds, and you just calculate that based on, as I say, the coax and the cable type.
All right. Thanks, Rob. And Jim, on your side, is there anything else we missed from the architecture, evolution, or profiles?
Maybe one more interesting technical point, and that has to do with a concept called synchronous Ethernet. So Ethernet switches are typically asynchronous. They have 100 part per million free running oscillators in them. But synchronous Ethernet switches are now available by pretty much all the vendors in the market. And they have better oscillators, 4.6 part per million oscillators, and it allows you to discipline those oscillators instead of free running them from the physical layer, just like we did in SONET networks. So this allows us to distribute an accurate frequency and recover and reconstruct frequency over Ethernet networks, but also almost all boundary clock functions for high accuracy applications use synchronous Ethernet in combination with the boundary clock technology, because disciplining those oscillators in the switches makes them much more stable, which allows us to pass the timing or reconstruct the timing and regenerate the timing on the PTP flows and the boundary clock functions with much higher accuracy. So synchronous Ethernet and the boundary clock functions for full on-pass support go hand in hand. And I think it's an important consideration from an engineering perspective that you include both functionalities if you're going to support things like 5G services, because all 5G radios, fixed wireless, or mobility applications are all TDD, time division duplex technology. They all require absolute plus or minus 1.5 microsecond UTC traceability. So this really helps if you're going to go through a chain of several switches or routers using boundary clock functions, helps us meet those boundary clock performance specifications and then the end user requirement as well.
I think that's actually a good piece of information to throw out, Jim, because at this year's Cable Tech Expo, there was a really good session on whether or not 5G is friend or foe. And it basically said, it can be your friend as a cable operator if you're the first to market. So if you're a cable operator and you're thinking about 5G, getting these switches that Jim's talking about is something you may want to be thinking about. I want to throw out there, Dari from the chat room said, and Dari, shout out to you. Thanks for joining. Testing PTP parameters at the RPD location is a good best practice. And we may have a show coming up very soon that gets right into how we test PTP. So that may be coming up soon. I do want to say, I want to give an opportunity to both Rob and Jim to promote anything you guys may have coming up or any new technologies or anything like that. Rob, Jim?
Yeah,
Jim,
sure.
I'll let you go ahead, Rob.
We have a website, of course, syncworks.com, with some white papers and lots of resources. So lots of good information there. So you can visit that site and reach out to us. There's ways to post questions, and we'll get back at you and help you with any network needs.
Great. Thanks, Rob. Jim, from you?
Maybe, Brady, it would be beneficial to explain the Syncworks Microchip relationship. So Microchip, we're the manufacturer of the cesium standards technology that Rob described, the GNSS, GPS timing receivers, the PTP Grandmaster products, etc. And then Syncworks is our distributor, where they resell our products. They provide support for our products and associated services. So they're our partner. We're the manufacturer and they're sort of the frontline troops. So that, I think, helps people understand the difference between, Rob and I and what we represent. I think personally for myself, I have quite a few articles lately, 5G Technology World articles. If you look that up, you'll see a lot of stuff from me on 5G timing. So if anybody wants to learn more about that, there's some good information out there.
What website do we go for that, Jim?
You should be able to get it off of just Google 5G Technology World, and they have a lot of articles, or you can get it off the Microchip website.
Awesome. Awesome. Well, Rob and Jim, thank you so much. This is a great episode. I really appreciate your time and all the information you've given us on PTP timing everyone in the chat room who joined to watch, thank you so much. There's really a lot of good chats going on, so I appreciate that. And please hit the subscribe button, give us a like if you enjoyed the episode. We definitely try to give you guys good content. So everyone, thanks so much, and tune back in next time for our next episode on all things DOCSIS. Appreciate everyone's time. So long, all.
Thanks, guys.
Bye-bye now.